Well, hello everyone. My name is Addison. I'm a PhD student at CISPA and maintainer of LibAFL, which is a project that I'll talk about a little bit greater detail later. Troy asked me here because I did some fuzzing on some cryptocurrency virtual machines a while back, and I guess you guys were happy about that. So here we are. So without further ado, I'm going to go ahead and get started. So what this talk is mostly going to talk about is kind of getting as far as we can, as far as we possibly can with fuzzing, and getting a better understanding of how we can actually use fuzzing to find new bugs in modern software. So just as a brief overview, here's what we're going to cover. First, we're going to talk about fuzzing conceptually, from a conceptual level, historically, some recent software testing advancements that we can tie into fuzzing nowadays, as well as some future implications about all those. And then part two, we'll talk about LibAFL to accomplish some of these goals. So let's get started. So first, we'll talk about fuzzing conceptually. So originally, someone came along and said, okay, our programs, they aren't doing well against unexpected inputs. We try the expected inputs in our tests, but well, that's not doing well for us in practice. So obviously the answer was throw random inputs at it and see what works. So I think this paper, an empirical study of the reliability of Unix utilities, is often cited as the first fuzzing paper. But the first instance of random testing I could find was all the way back in 1971, used to test circuits. And this strategy is still being used to this day, both just repeating the original studies as well as for some new work as well with prop test in Rust and fast check in JavaScript. So at this point, fuzz testing really just means random testing. We can generate inputs really fast. We don't need any feedback from the target except did it crash. And if we need to test something which is a little more complicated, we can use dictionaries to kind of fill in magic bytes where we don't know exactly what we're going to need to fill automatically. Problem being, the inputs that we generate aren't always so meaningful. We generate a lot of garbage data. So we're more testing the parsing aspects of our programs. And if we do get past the parsing aspect, that only happens maybe once in a million times, and we waste a lot of cycles. Similarly, we can't tell if an input is actually useful for what we're trying to test, right? Sure, we can tell if the program crashed, but that doesn't tell us if an input is meaningfully different than another input. And this also, in turn, prevents us from generating larger structures or structures which have relative meaning, like having a length field followed by a buffer determined by that length. Right? These are very difficult problems to solve with just black box generative fuzzing. So here's where we are so far. We've got crash oracles. The crash tells us that our program has a bug. We have dictionaries to kind of fill in the gaps of our random input generation. Not so much happening yet. Okay, so we've solved the problems that can be instantly detected by random input generation. Great. But we're still having these rare unexpected scenarios where we're having crashes or memory safety issues induced by just unexpected inputs. So let's talk about fuzzing just from a super high level, right? So consider an input space, right? So just the space of all possible inputs that we could possibly generate, right, that are valid. So concrete inputs in this space are single points, and we can divide this into regions. So this region here representing all of the inputs, somehow related to hello one. They have different meanings, and they potentially describe the input or the behavior of the program or whatever. Right? They can overlap, they can border each other, they can encapsulate each other, or they can be entirely destroyed. And these regions we can define with something concrete, such as something we can observe as part of the input, or something we can observe by watching the execution of a program under test, right? So let's go a little further, right? let's talk about mutations conceptually, right? We have some base input, and we want to generate new inputs that are very similar to this input, but still potentially interesting and new. So for example, we might mutate this input hello1 into hello18 by appending an 8, right? So we can generate lots of different mutants, some of which will actually be able to trigger defects, like that region indicated in red, but many of which won't, right? And going from here, we can kind of describe a region around the potential mutants, or the space of mutants that we can generate from some base input, right? So note that in this case, we were lucky. There's a defect region that's reachable after a single mutation from this input. So in our hypothetical scenario, this input here, as a result of our mutation, ended up in that defect region, and it triggered the defect as something we could observe. But we have this other defect region over here, which is untouched, and we can't mutate our input in order to get to that defect region. In other words, the mutations that we're applying right now aren't strong enough to get us there. So we'll never find it, in other words. So with mutation alone here, we can't find the second defect region. To do so, we want to use mutation on an input that was generated by a previous mutation. So how do we decide which input to use? Well, that's where novelty guidance comes in, as I'm sure everyone doing fuzzing is familiar with at this point. Suppose we have some defect region that we want to hit. There are other regions that we can observe, such as these, which I'm going to pretend are code coverage. Obviously, this is just a magic visualization, which is a bit contrived. So we have some base input and its mutation region. When we mutate our input, we can observe which coverage regions we hit by that particular input. In many cases, we're not going to find new regions. But if another previously unseen region is hit, we consider the input as interesting and retain that input as a new mutant that we're going to then mutate further. This input may generate other uninteresting inputs because now this coverage region that we've hit once, we mark no longer interesting. But with sufficient time, this strategy can explore the coverage space of a program and can be used as a general strategy in order to search the input space of the program, eventually allowing us to find the defect. So now we have a strategy for actually exploring the input space of a program, right? We can progressively search for new behavior. These mutations allow us to take known good inputs and basically slowly crawl our way throughout the input space of the program. And we can even do fancy things like observing comparisons that happen in the code in order to guide which mutations to apply next. Unfortunately, these search strategies may not find the new behavior, right? And also, we don't have a guarantee that a coverage region entirely overlaps with a particular crash, right? We know that if we have some crash, right, we know that the code responsible for that crash was hit. But if we hit the code, that doesn't necessarily mean that we trigger the crash. And for the comp observe and replace, we can only directly replace bytes that we know are to be compared, with some exceptions. Okay, so moving forward, we've got some new ideas and we're starting to build off of old ideas. We want to generate new inputs that are able to test our program. And now we have some better strategies for actually testing the program by generating new inputs progressively. Okay, great. Moving forward, we can even go a step further and try to detect new kinds of faults that we haven't been able to observe previously. So, for example, we can always detect a segmentation fault because that triggers a crash in the program. But with a little cleverness, we can also track when a buffer is overflown, even if it doesn't trigger an immediate crash in the program. And this can help us find potentially unsteady states in the program where a bug is introduced, but doesn't necessarily induce a crash on every input which has this particular bug being triggered. And this is great and all, but how this works is that the sanitizers will tell us when some safety guarantee is invalidated. And that's generally not going to be program specific. That's going to be something where it applies to the entire type of program that we're trying to test. So for C, we're looking for memory safety issues with a lot of these sanitizers, for example. In some fancy cases, we're looking for the injection of commands or stuff like this. And they generally only verify this implied safety mechanisms that are guaranteed by, or that should be guaranteed by the programmer regardless of the application. And a lot of the time, these sanitizers are flagging things which will either become a crash later or will generate such an invalid state that we'll observe some kind of other side effect later. So it doesn't necessarily help us all the way. So with all of this happening now, we've sort of entered this fuzzing renaissance that's been referred to in the past. If you read some of the blogs from the original AFL developer, this is what he refers to it as. And as we go on, we have more and more new ideas being introduced. We have strategies which improve on existing strategies using these new ideas. And this is all great, but there's a problem. And that is that we're still guiding by coverage a lot of the time, right? And here's some ominous academic results that might be important later. Fuzzers that are best at finding new coverage aren't necessarily the best at finding new bugs. In other words, this is a conclusion from what we saw earlier of crash means code's hit, but the code being hit doesn't mean that the crash occurred, which means that a lot of the time we're still not finding bugs. But okay, that's fine. We can't find everything. Let's just say not a problem for now. Let's move on. Okay, we've resolved all of the memory safety issues. We live in a perfect world where memory safety is no longer a problem anymore. But we still have unexpected behavior in our programs, right? There are kinds of bugs that are more than just memory safety errors, right? So now we need to look for those kinds of bugs. So we have our two bugs from earlier where we're triggering some address sanitizer or we're triggering some crash in our program. But now we want to find situations where our program under test gives us access to a particular resource when it shouldn't be, right? This class of bugs can't be found with the memory safety sanitizers or with memory safety oracles because it's not triggering a memory safety error. It's triggering a business logic error. So how do we find these? Well, I'm sure many of you who are in the fuzzing space more dramatically are familiar with these differential oracles where if we have two implementations of the same system and we have a guarantee that they will be equivalent at the end, we can test them both by executing both and seeing if their output is the same. So in this case, kind of a contrived example, we provide our input to implementation 1 and implementation 2. They both give us an output regarding the authentication status of a particular program. I know I said authentication and not access. I'm just realizing that now, whatever, it doesn't matter. And we see that, okay, one program says access denied, and the other program says access granted. And we know that these are two incompatible states, so we know that at least one of the programs is wrong, right? And this is great. The programs differ, we know one is wrong. These comparators are generally quite simple to implement, being like an EQ that's implemented by the developer originally. And if the other implementation already exists, we kind of get this for free. Problem being, any cases where the program isn't well defined, we will have differences that the developer won't care about. So I've been fuzzing a lot of regex recently, and two implementations of the same regex engine don't necessarily have to have the same behavior in all situations where the behavior is not well defined. We can talk about that in greater detail later if you want. Sometimes these comparators can be too sensitive. So if we have something which generates some kind of non-deterministic data in the output, and our comparator flags that as an error, then that's going to generate a lot of false positives for us. And of course, all of this requires us to have the other implementation in the first place, right? So these are some pretty strong assumptions to start with, and this ends up not being super useful for every program in practice. So how else can we find these other non-memory safety business logic errors? Well, we can start to use property oracles. So these are oracles where we can actually process an input in multiple sequences and see if some invariant of the program is preserved over that particular execution. So for example, right, suppose we have a formatter implementation, right? And we want to make sure that our formatter isn't introducing new parse errors or linter errors, right? Well, we can do that because we know that before the input is formatted, right, we can run the linter on the original input, and then we can run the linter on the formatted output. And if we observe that there are new lint errors inside of the output from the formatted version, we know that there's a bug somewhere in the formatter, or that there's some mistake in the part of the linter where it's not detecting a linter error where it should have. And this is due to some contract that the formatter gives us about how it will behave when it performs formatting. Similarly, we can do things with encoder-decoder pairs. If you're ever working with a compression and decompression library, we can test if the decompression works as expected by compressing some input and then decompressing it and see if we get the same input back, right? If we have a parser and an unparser, we can check that the parsing is idempotent, right? We can check that if something is parsed and then unparsed and then parsed multiple times, it doesn't, have unsteady states where it's growing or changing its interpretation over time. Now what this means for us is that fuzz testing is now invariant testing. We can look for violations of contracts that the program gives us. And this can be used in a lot of different scenarios, as I'm sure many of you are aware of. If we can define a contract that the program gives us, then we can check it. It gives us so much opportunity here, and we don't need a second implementation. The problem being, we need to be able to define that contract explicitly and universally, right? If we ever have any situation where the contract doesn't hold for particular inputs or in particular situations, right, we need to know and be able to quantify those exceptions so that we can ignore them. Otherwise, we get a million false positives. Obviously, we need a contract. And if we're testing a particular piece of software, we need to be able to actually be exploring code regions which are relevant to what we're searching for. If we're testing inputs that don't even trigger some kind of invariant that we want to test, we're wasting cycles just like earlier. Okay, problems for a later date. Now let's look at our big graph of fuzzing advancements again. Now we have this new idea of pulling in these software testing oracles into our fuzzing infrastructure. The only problem being that we have a bunch of existing work to optimize for these crash oracles, which are strongly correlated with the coverage of a program. And now we have these new oracles, which aren't necessarily as strictly related. And this actually shows up in practice. We had a fuzzing paper that we submitted to the fuzzing workshop last year, where what we observed is that with these higher complexity oracles, right, where we're looking for bugs that are necessarily requiring more complex inputs or complex state in order to trigger, the coverage bug agreement between fuzzers went down further. In other words, fuzzers that were rapidly exploring the code were significantly worse at actually being able to generate inputs that triggered these bugs. The exact reasons for this are as of yet unclear. Perhaps we've overfit to crash oracles, or we're relying too heavily on this existing idea of coverage. But since all of these kinds of bugs are just higher complexity, what that means for us as security researchers from a memory safety perspective is that it probably means that we're missing a lot of memory safety bugs as well that are just significantly more complex to trigger using fuzzing, right? And this is somewhat an obvious conclusion, but that doesn't necessarily need to be the case, right? Right now, we're using these strategies which are heavily dependent on this underlying assumption that bugs will be found if we can find the code regions that trigger them. But we're finding more and more evidence that this isn't the case, not just with these new classes of bugs, which are discovered by differential or property oracles, but also with memory safety bugs. On the screen, you can see some discussion about this. I just realized I've totally bungled that text. I'll fix it later. But we had some discussion about this WebP bug that happened recently, where we'd been fuzzing WebP for thousands of CPU years, and yet never encountered this Huffman routines bug in WebP. And Van Hause, who also is an AFL++ developer, commented, "I can say there is no chance in hell a fuzzer could find this from scratch." Right? How do we fix that? Can we fix that? Is this something we can approach as an automated strategy where we can find these well-definable issues in programs in the future? And what I think that's going to require is significant rethinking of how fuzzing conceptually even works. We need maybe better mutations, we need maybe better coverage, or a totally new strategy for guiding entirely, right? Okay, so now that I've given everyone an existential crisis, I'm going to move on to talking about LibAFL. We're sort of rethinking what fuzzing is conceptually from the start. So let's back up. Early on, we talked about how we are using this idea of an input space, and we want to explore this input space such that we find inputs which trigger defects in our target program by generating concrete inputs for which we can observe some known undesirable behavior. In most cases, memory safety, but with these new strategies as well. So ELDR, we have inputs that we want to generate somehow to test for some observable objective, right? So we have some search objective that we're trying to get to, and we're trying to generate some path in order to get there by way of mutation, in which case we need some observable way to know if we're making it towards those defects or if we're making our way towards new regions of the input space that may contain defects, or we need to find a better way to generate inputs as a whole. So how we've done that so far with the modern fuzzing pipeline is we have some input scheduler, which is pulling inputs out of a corpus of inputs, out of a set of inputs that we've already found. We mutate those inputs. We have to execute those inputs to see if they actually generate our objective, which in most cases it crashes. If it crashes, we throw it into a list of inputs which cause crashes. Okay, let's say it doesn't. We throw it into a list of, we throw it back into our set of inputs to be mutated in the future if we see that it generates new coverage. Okay, let's see if we can abstract this a bit and pull ourselves away from relying on this very fixed set of stages in fuzzing. So how libAFL works is that we define components, and then you can sort of use these components however you wish in order to find whatever your search goal is in your program, right? So first we define a state, which represents a container for metadata that we're using to observe the program under test, as well as some, as well as a corpus for the inputs that we're going to use in the future, if desired, or and a corpus of inputs which we mark as solutions for a particular search problem. And in this case, our inputs don't necessarily just have to be sequences of bytes. They can be defined however you want them to be defined. In order to actually pick which inputs we want to use, we define a scheduler, which just tells us which input to use next by interacting with the global metadata that we've collected so far, and then pulling an input from the corpus. Okay, then going further, right, we define stages, right? This is effectively just do something with the current state of the fuzzing pipeline, right? The current state of the search pipeline, if you will, right? Where we're just generically we're generically defining this perform function. We'll get back to that with an example in a second. And then in order to actually observe some kind of behavior in the target, we define a type, or sorry, a trait or interface for those of you who aren't familiar with Rust terminology, such that we define observers that are named that can then be interacted with by feedbacks where we're collecting some kind of observation during the execution of our target and then processing it with the feedback to determine if it's interesting, either for adding to the input corpus or adding to the solution corpus. Okay, how does this work in practice? So as an example, here is our implementation of the mutational stage, which is effectively the traditional fuzzing concept, right? So what we do is we load our input from the input corpus, we duplicate it, we mutate the duplicated copy, we then execute it, where the observers will take some information during the execution of the input, and then we evaluate the result of that. We evaluate the result of that execution. So what happens there is that we have a set of feedbacks which process the observers for whether or not it is an objective, and we have a set of feedbacks which process it to determine if it's novel to be added to the input list, right? Okay, and then if it's marked as interesting by the objective feedbacks, we add it to the solutions. If it's not added, if it's not marked as an objective, but it is marked as interesting by the feedbacks which determine novelty, they'll add it to the input corpus. And this happens in a loop, and this acts as a single stage in our pipeline. Then the fuzzer itself is just a sequence of stages that you define and that you pass to the fuzzer in order to be executed. So what ends up happening is that every time that we want to process a single input, a sequence of stages is triggered, which will try to process that input, such as the mutational stage from earlier, and then go back to fuzz one once those set of stages complete. And with this strategy, we move away from simply thinking about fuzzing in terms of it's a novelty search algorithm that is looking for inputs which crash by guiding it via coverage, and more towards a general purpose search algorithm. With this way, we can define whatever we want, whatever kind of search algorithm you want, as a fuzzing pipeline. It's rabbits all the way down, right? And just to show you how flexible this is, right? If you're familiar with Sokoban, the puzzle game, which is, as you can see on the screen, you're a warehouse worker and you're trying to push crates into desired positions, I actually wrote a fuzzer using LibAFL, which accepts Sokoban puzzles and issues an objective whenever it solves the puzzle, right? So let's look at that, and let me change my screens real quick. I'm going to have to stop presenting and then represent again. This guy. Let's see. Okay. Don't mind the warning. That's just because I don't code good. Okay, so we have our puzzles, which I'll show you how they're generated in a moment. But if I run, I need to run this with stable. What this will do is it will go through and it will pull puzzles from a puzzle generator and try to solve them. So give it a second to build because I forgot to actually rerun build. Sorry about that. Linking always takes forever on Rust. That's my bad. Go ahead.
So presumably your objective function is when all the circles are covered. Is that right?
Right. So I'll actually show you how this is implemented in a second. But go ahead.
If I understood your diagram earlier, you also need a novelty function. Is that right?
Right.
So what would be your novelty function here?
So my novelty function for Sokoban puzzle solving is if the regions defined by what is reachable by the player changes. So in other words, if I have a set of crates that are on the screen, right, what will happen is there is a region of space my player can actually move to, right? So what will then happen is that my mutations are defined such that one mutation is the player goes to try to find how to move a particular box in a certain direction. So it basically attempts to find a path such that it picks a randomly selected crate in order to move it in one direction, or if we can move that crate all the way to its terminating node, right? So if we can figure out how to move one crate to one particular solution spot, right? What's actually really fancy schmancy about this is that this is actually a snapshot fuzzer, where it's basically queuing all of the moves that it's going to perform. So each input here, so we can actually look at this. So I've defined pretty much every kind of type that you can define with LibAFL as a custom type in here, and I'll link this as well in my talk. So if we look at the definition of the input itself is just a sequence of moves, right? And then what happens is that every time that we execute, we would want to run those sequence of moves, right, and see if we get into a state after those sequence of moves that represents a solve state. But in order to do that, what I actually do is I save a hallucinated state, right, which is basically we know that up to a certain point in the move sequence, right, we've already done some set of moves, and it will always be the same result up until that state. So in order to optimize a little bit, what I do is that every time that I mark an input as novel, it saves the state at the point at which the move stopped, because I only ever mutate by adding new moves, right? And then when I resume, basically the executor pulls the state from the input and then applies the new inputs there and sees if it's novel or if it's a solution state. If it's a solution state, it's added to the solution corpus as the full sequence of moves. And if it's marked as a novel state, the state at the end of executing the most recent moves is saved as part of the input for it to be processed further, which I think is pretty nifty. And it's able to solve some pretty gnarly puzzles pretty quick. So let's take, for example, this puzzle 12 here. So I can actually just show you with a visual representation rather than a text one, because text is disgusting. Let's see. Level 12. So let me change the screen that I'm sharing once again. At this point, I really should just share my full screen, shouldn't I? That one. Oops. Which screen do I have it on? That one. So this level 12 here corresponds with this level. This is the generator that I'm using. And I've somehow loaded the wrong seed. What did I do here? What is the seed that I used? No, I randomly generated. No. Okay, it's 0. Okay. I don't know why it's ignoring my seed function here, but okay. Weird. I tested that earlier and I guess it didn't work anymore. But in any case, we can define novelty algorithms or novelty representations for each component there. So if I go back, and I shouldn't have stopped sharing, I don't know why I did that. I can actually go to my definitions for my observers. Source observer. And this basically will just tell me, it literally just takes the state of the Sokoban after the execution of that particular sequence of moves. And that's the observer that's defined. And then what will happen is that that's processed by a feedback, which then tells me, okay, one of them says, okay, is it solved by just checking if all the crates are on all of the blocks, right? Or all on all of the destination points. And then another one tells me if the puzzle is still solvable. And there's some pretty clever strategies that you can use to determine the solvability of a puzzle. And then the other one is just some statistics about what is the current flood fill status of the input? What is the current representation of where the player can reach? And also, there's one which just literally takes the hash of the current state of the puzzle and sees if it's new. But I don't use that one in practice. But yeah, you can define it pretty much however you want, in other words.
Sorry, was that a summary of an answer to my question?
Yeah, sorry. I'm going to open source this afterward, or it is already open source. So you can find it. I'll link the slides. But yeah, it's pretty extreme use case, I would say, of LibAFL. But it kind of demonstrates what I'm trying to show of if you want to define a metric by which to fuzz something, you can do so. I implemented a new observer today for whether or not, or a coverage metric for the largest index observed being accessed from a particular pointer. So if we have a base pointer and we want to measure if we dereference basically by doing an array access, I just registered the LLVM callback for this particular kind of coverage, and I define it. Let's see. And then I literally just defined this as an observer today. About 5 hours ago, I was like, hey, what if we did this? And I just kind of threw it in, and it's already being used on a variety of things. Or I can just use it to fuzz image parsers, for example, where I'm maximizing over the generic element pointer, or I can't remember exactly what it's called, but figuring out which element in an array is being accessed, right? And just as an example, and you can do much more complex things, of course. And you don't have to stick with just C programs, right? I know some people who are developing embedded systems fuzzers with libAFL, or who are developing snapshot fuzzers for Linux on it, right? You can define the executor however you would like, just as I defined an executor for Sokoban. Go ahead again.
So how does it, so it sounds like what you showed, there's sort of like a binary sort of classification, either it's interesting or not. For stuff like maximizing the like index, like sort of how do you handle sort of relative interestingness? Like in libAFL, like is that just like a schedule priority thing? And like do you have to have like, I guess like one could imagine like some sort of like, I don't know, like ramping scheduling, because you still want to schedule stuff that's like less interesting, etc.
Right. So you could define a scheduler, for example. I don't know if I define a scheduler for Sokoban. Let's see if I do. But yes, you would just define a scheduler, and then you could set some metadata associated with the test case that tells us its relative interestingness, or maintain a table that says, okay, well, here's the relative interestingness of each input that we've currently observed. Let's see, Sokoban fuzz. And I do define a scheduler. Let's see what I did. Yeah, so my scheduler currently optimizes for the number of crates which are currently located on targets. So basically it uses the general assumption that you are closer to a solution when you are having more crates on your destination points, which is not necessarily a good assumption, but it works for many puzzles.